Bonjour à tous, buenos días, egun on guztiei, eta eskerrik asko gurekin konektatzeagatik. Eta ongi etorri FComp proiektuaren azken saioa. Merci de vous être connectés à cette session finale du projet FComp. Aujourd'hui, nous avons un public de la France, d'EUSKADI, de Navarre, mais malheureusement, on ne parle pas tous de français, espagnol ou basque. Alors, donc, nous allons garder la session principalement en anglais. Okay? Let me say hello to everybody and tell you that you can ask the questions because I'm only saying hello. Okay? This is Martin from HEGAN, the Basque Space Cluster, one of the partners of this project. And just to comment, you can ask your questions in the question time, both open your microphone and camera and ask the question, or using and writing to me using the chat that you can see in your system. Just say hello. We are going to hold this final session of the FComp project just to show you the results of the project. All our partners are here today. ESTIA, the University of Advanced Industrial Technologies of Bidart, MICROLAN, one of our members, one of our cluster members, an industrial company specialized in precision machining, and the Leyre NAITEC technological center specialized in mobility and mechatronics. At the end of the session, we will have a few words of Ms. Leyre AZCONA, who is in charge of projects of the Euroregion. The Euroregion NOUVELLE AQUITAINE EUSKADI Navarra is the framework program that we have been co-financed. Okay, so from this moment on, we give the floor to our leaders, NAITEC. I don't know who is going to talk, Fernando or Angeru, but okay, open your mics and thank you very much.
Yeah, I will start, Fernando Varela. Merci Martin d'avoir lancé l'événement. Je m'appelle Fernando Varela et je suis responsable de la diversification au centre NAITEC. Et avant de commencer à discuter les détails du projet en anglais, je vais dire quelques mots en français. Je suis pour payer gratitude à nos amis de ESTIA et de l'Euroregion d'avoir la possibilité de faire ce projet. La motivation principale pour faire ce projet vient de l'idée que les parts sont moins que les tout. Donc, la offre technologique commune naît du travail entre tous les partenaires de la trois régions pour offrir plus que ce qu'on peut offrir seulement chacun. Donc, le résultat de ces projets n'est pas qu'à prouver ces réalités. Réunissant un centre entreprise avec un autre niveau de capacité comme MICROLAN Aerospace et la vision et l'expérience du cluster HEGAN a fait possible ce projet, a fait possible de réussir et de trouver tous les résultats qu'on va présenter aujourd'hui. Ensuite, on va expliquer vraiment les grandes lignes du projet, de la présentation tous les partenaires. Donc, thank you very much. And I was saying that the motivation of making this project comes from the idea that the parts are less than the whole, and that the technological offer we can reach, joining together all the capabilities of different centers, are more important, more interesting than the offer we can offer by ourselves. So let's start talking a little bit about the concept of the project, and then all the main lines of the project, make a brief introduction of the partners, and then I will give the word to Angeru, who will follow with the results. Okay. So if you can move on, The concept behind the FComp project was trying to join the capabilities of the different partners in composite industry and flexible electronics on one side, and precision machining. We needed to bring these electronics practical and available for a specific product. So the process behind the FComp project lies on the capabilities of doing flexible electronics of NAITEC. We have more than a decade of experience in making flexible circuits, and the ability of the composite industry to make, pile up and lay up different layers of these fabrics, of these technical fabrics. So it's possible to embed these electronics within the process of performing these composite parts. And so we can bring new functions and new ways to include wiring, sensing, and other features inside the composite. However, in most of the circuits require some connection to the outside, some connection to an outer circuitry. For example, in sensing, you need some touch connectors, so you can actually measure the signals arising from the sensors. So for that reason, MICROLAN Aerospace bring all these capabilities and knowledge how to do precision machining on the composite to avoid all the problems and difficulties arising in this operation, and leaving the circuit open to further operations. It was foreseen. We tried also with our partners to build up some 3D connectors made of metal. That wasn't very successful, I must say, but we need to give a try. But however, the results and the process of flexible electronics composite machining has been shown as a success, and we are now in a position to offer this technology share between the different partners to companies and specialized groups where this task is needed. So this is more or less the concept behind the FComp. We need to do a lot of work choosing materials, choosing different technologies, and how to do this composite, how to do this circuitry. So we will show it briefly in the next minutes. But now let me introduce in more detail our partners. So Martin, please. We start with the centers at both sides of the Pyrenees. There are two centers. One is NAETEC, which is located in Navarra, in the Navarra region. It's focused on mobility and mechatronics. So we focus our attention in the way, this new way of moving, how to electrify vehicles, how to share information between the infrastructure and the vehicles has to be done. And within all this framework, we develop all these flexible electronics for the automotive sector mainly, where we can include all these electronics within mainly interior parts or other plastic parts that you can find inside any car, like headliners, seats, rooftops, etc. On the other side of the Pyrenees, there is, as I said, was COMPOSITADOUR, which is the technological platform promoted by ESTIA and the École Engineer. And COMPOSITADOUR stands as a brand where they provide this high-tech equipment and mobilizes network of skills around the composite. So they can do anything from scratch, from the piling of the different fabrics to the post-process, non-destructive testing. So they are very skilled, very well focused on the composite, and the great partner we are looking for to bring these electronics into the aeronautical and aerospace industry. Okay, so MICROLAN Aerospace, it's a company. It's a relatively young company, started in 2004, and within few years started as a very high skill, very high focus precision milling and turning operation for two main sectors, which is more aerospace. They are already have parts manufactured by them that are actually flying in different operations in aerospace, as well as what is called the science industry. They are providers, suppliers of the CERN laboratories since a decade now. So they are very high skill, and this is an example of the degree of precision they can get in their work. And last but not least, HEGAN bring together to the consortium the view of the overall industry. HEGAN comprises a lot of companies on the Basque Country as well as in Navarra related to aeronautics and aerospace. So they could bring to the technical partners a very good clear view of the state of the art on what are the needs and the requirements of these companies. So it helped a lot in the beginning to focus our activity towards real problems, and also following up all the developments by a strong diffusion and dissemination activities around the FComp. I can remember some meeting we did in December, which I found very successful in the Basque Country, and unfortunately, due to the COVID restrictions, we were unable to repeat in the other regions. But I hope this webinar will help to catch up and to show all the results to all of you. So this is more or less the brief introduction we want to make, and now I will pass the word to Angelo, who will together with the other partners, they will show the results around the FComp. Thank you.
Well, hello everybody. First of all, we are going to show you a video that summarizes, we think, quite well what has been the development of the project. So, Martin, whenever you want. No, Martin, we do not hear the audio. No, please. Okay, so hello again. Hope you have enjoyed the video. We think it's very explicative images of what we have done in FComp. And now what I'm going to do is just trying to go more in the details of what we have shown in the video, okay? As Fernando has explained in the presentation, the initial idea of FComp was developing the embedment of sensor in composites by doing 5 tasks that are done in a row. First, building a sensor, embedding it in the composite, then machining for revealing the contacts, for putting some capper on these points, and later on manufacturing the final contacts. This is the initial idea. This putting a little bit in the ground. The idea is just taking, as said, one sensor. You can see in the image on top, just and put it in between different plies of a composite material. For that, we need to make first the design of the sensor. In this case, we have decided to do a strain gauge sensor with three gauges. This is just for the purpose of having a sensor, but indeed we can put whatever other design. The design as well included not only the part of sensing, but as well how the connections goes outside. After having this initial design, the project goes into a trade-off for the material and process selections and the manufacturing. You can see in the image middle below all the process that we have to follow, where we needed to do some iterations that I later on explain. And finally, we verified that our full design is okay by doing some testing, mechanical tests mainly, and as well some functional testing. So let me go step by step, explaining what we have done. First task was the printing of the printed circuit. This is a task where the leader was NAETEC. In this case, we follow a series of trade-offs, starting with first the sensor design. In this case, as previously explained, we selected an strain gauge. We make the detailed design of the sensor itself plus the contact, and we started as well with iteration because the thickness of the tracks is something that is related as well with the capacity of the process for manufacturing the track with the ink. So we make a trade-off between different thickness, reaching to approach where 70 microns of thickness of the track was selected. The image that we have in the middle, those small tracks, those are 70 microns. As said, this is linked with the selection of the ink. We make a trade-off between different inks that we have in-house as well. NAETEC has very good relations with some companies manufacturing inks here in Navarra and so. And then we did this trade-off of properties of the ink that as well is related with how we do the process. I mean, we need to prepare the surface material, we need to add additional dielectric material, how many layers, how we put it in the oven. I mean, this is very iterative, and as well, and mainly related with the substrate that we use. We have tried with 2 or 3 types of paper. We have used carbon fiber, glass fiber, and polyamide, Kapton, for doing the trials, because some of them have good properties for some things and the others for others. And finally, we have reached to a conclusion that the best balance is one of those that I will say now is the Kapton. Okay. We found as well during the project that we needed to define some details like the connections, because it was, you will see, some points has not been as good as we wanted, and we finally needed to look for a solution. You can see in the image, just with adhesive glue, conductive glue, putting some connectors. We needed to make some kind of details that later on we further explain. We finished with a batch of about almost 200 samples of different materials. You can see in the image in the top. This is the left one is fiberglass. In the middle is carbon fiber. Paper on the right. Bottom left is Kapton, and bottom right you can see 3 samples done in carbon fiber with the detail of the 70 microns track. We took this almost 200 samples to COMPOSITADOUR, so they can start with the embedding in the composite. First of all was the selection of the material to be used. In this case, it is an unidirectional carbon fiber prepared, very common in the aeronautical sector, and COMPOSITADOUR is very familiar with it. So for them, it's let's say easy now to work with. This material, after doing the stack up, is sent to cure in the oven at 180 degrees with 7 bars at about 2 hours, and then we get the final samples just with the sensor embedded in the composite. And with that, we started to verify what is the best solution of substrate by checking how we, or with sample, we minimize the mechanical impact and the delamination problems. First test that we did was the tensile test. In here, we saw that, well, you can see in the graph on the right, there is some reduction in the mechanical performance. For checking that, we prepared some coupons without the sensor inside, so it was taken as the reference that you can see the column most on the right, and you can see how, depending on the substrate, the maximum tensile strength is decreasing. In here, we saw that the most promising was the papers with different grams, and even with them, we have a reduction of about between 7 to 18%. Even with the polyamide, we have this 18. In any case, below 20% reduction of the properties of the full part. Second test was checking these samples against bending. In here, we saw as well the same issue. In this case, we have the reference on the left. Sorry for these mirror images. And you can see as well, there is a decrease in the performance, in the mechanical performance of the material. But again, pharmacy paper is the one that has less impact, only 4% reduction. But for example, if you go, the column that is more in the right is using dry glass fiber, and here we saw a very big reduction. Why? Because the resin was not properly transferred because it was dry fiber put in between the pre-preg. Then the resin didn't go between the dry fiber, and then we didn't manage to do the proper shear transfer between the different plies. For verifying these findings, we built some finite element models to see if what we were seeing was caused by the material, by the test itself, or whatever. We verify with this comparison between the coupon and the sensor examples that, when we put a sensor in a certain position of the composite, in this case, when the sensor was placed almost in the most outer position of the layup, we saw that, okay, we started with a symmetric and balanced solution. When we put the sensor, the final stack up is unbalanced. This makes that even with a simple tensile force, you see a deformation. So we already need somehow to balance this. And related with the explanation that I gave about the shear transfer, in the bending test, this is clearly how, if depending on the substrate, we don't have a very good shear transfer, the bending test fails quicker. This is because we get like the two materials separates, just being the separation, the sensor, and then it breaks the part that is thinner, and then it breaks the other part. So this is the failure mode in the bending test. Another check that was done, apart from the mechanical ones were the functionals. In here, what we saw is if the ink in the sensor is not completely cured before putting the sensor in the oven for doing the composite, it gets cured inside the oven. This has an issue because as the ink is covered with the electric, more fiber, and so the curing process is not very good. So what we see is that there is a degradation in the resistance, but we don't go to the proper resistance. So this is something that we have already solved. We have seen how to do that, but it's something that we have realized that it's important to have, for an escalation of this process, a very adequate curing of the sensor before putting it in the oven. With other substrates, for example, with the paper, the issue was related a little bit with the CTEs of the different materials that cause that deformations between the different layers, the carbon against the paper, makes the ink crack because the difference in the deformation generates stresses inside, and the tracks are broken. So what we have is, you can see in the bottom line, insulation problem. So we started having some resistance in the track, and finally we have zero. So it does not work. So this is why, even if the papers were the most promising solution in terms of mechanical properties, in terms of functional, we have to discard them. One of the other points that we check is trying to verify where the sensors are, so that we can machine later until getting this sensor out. We see in the photo on the right that depending on what is the substrate, the image obtained in the ultrasound analysis is different. And this test is done by COMPOSITADOUR. They use a 10 megahertz probe. And the idea is that the conclusion is that maybe using a higher frequency probe, we will get better results. But this is something that, okay, will be done in the future. Another point you can see in the next photo is if the sample is larger, it's easier to detect where is the sensor. You can see 5 sensors inside each of the laminates in the image, and as well, depending on which is the material of the sensor, it is easier or not to detect it. So as a conclusion, and Anais, whenever you want, you can interrupt me and add whatever you consider it is needed. Okay, and then the main conclusions from this task is that okay, the mechanical properties of the full composite are reduced, but it's something that can be somehow improved, and by design of the way of producing the material, and by the design itself at the preliminary stages of making a component. The integrity of the sensor, as explained, is improved by getting a proper cure of the sensor before putting it in the oven with the composite. And for the location of the connections, it is needed to add probably some reference for having a better machining, and even using an automatized fiber placement will help to do that. For this, for example, COMPOSITADOUR has a lot of robotics experience, and for this automatized fiber placement, they have contrast that is something that could help. In this case, for FComp has been done manually, as you have seen in the video, but this is something that could be added in next projects. For task number 3, that is the revealing of the circuits. In here, the leader was MICROLAN Aerospace. In here, as per the use of composites, there are 2 main issues. One is the anisotropy, that makes that the fracture of the mechanism, the fracture mechanism of the part when doing the machining is different depending on how the tool goes against the fiber. So that generates different angles. So we have different braking mechanisms. Another point is that the fiber themselves are very abrasive, so it makes that the tool wear is very high. For solving the issue of the anisotropy, we need very sharp cutting tools. But on the other hand, for solving the highly abrasive problem, we need to put some coatings on top of the cutting edge that reduce this sharpening of the edge. So it is needed to do a balance of these 2 things. The problems that MICROLAN has found in the machining, you can see in the image bottom right, there are different trajectories or different ways of trying to do the same machining. Some are more promising than the other, but broadly it can be concluded that we have delamination if we do not eat it properly. You see that the samples in the middle are more damaged than, for example, the ones on the right. There is uncut fibers. That is something that has to be solved because they can produce micro cracks. And the deformation of the part when doing the cutting is something very important, as it generates as well the imbalance of the part, generating deformations that are unwanted for a proper mechanization. Another point that was included in this task is trying to reveal the contact points for doing the additive, the next step, that is adding the copper to the contact. So in this case, MICROLAN used a drill process for trying to reveal the position of the contact, and for this it was seen that not having a reference, an external reference, or not having considered it since the beginning makes that it's very difficult to reveal the contact, as it is not possible to take a proper reference. Regarding the wear of the tool for the drilling, as per MICROLAN's experience, is not a big issue. Guillem, later on, if you want to further explain, we will have a moment. Okay, I continue with this, and later on we go in further detail. As well, taking the opportunity that in COMPOSITADOUR there is a machine by Bayab that makes the abrasive water jet machining. We did some trials. Okay, this machine just use some nozzles that they put water containing garnet particles at a pressure up to 800 bars. So, and it moves over the surface, generating, you have seen in the video, that remove part of the surface just by abrasion. The point in here is just selecting what are the proper pressures and what is the speed of the movement of the nozzle. This way, you manage to have more or less revealing of the surface. You can see in these photos what is the final aspect of the samples. It is not completely smooth, because as you can see in the explanation in the image on the top right, compared to the conventional machining, this introduced just a delta of the thickness machine. And so this means that if we don't have a completely flat reference surface, we are going to transfer those irregularities to the final part. This is the reason why And you can see in the image in the bottom left that there are some parts that are completely revealed and other ones that have still some carbon, that is the black parts. So, but in any case, the solution is promising. By adding some additional copper plates, for example, in the sensor at the initial phases, could improve this kind of solution. Fourth point is with this part reveal, adding recharging material to the sensor. This is as well leaderized by COMPOSITADOUR, and they have in their own facilities the company called Cometa Technologies, that they are experts in doing this kind of metallization. And in this case, the process has been as well a bit iterative. First, we saw what was the influence of the substrate when applying the process. In this case, the process is quite aggressive. So we saw that for the polyester substrates, it was completely destroyed. It's photo on the left. There were some copper in the substrate, in the capton a little bit more, but not too much. Even adjusting later on what is the type of nozzle, the pressure, the gas flow, and so it was seen that very few adhesion of the particles could be granted, because even when you pass one time and go back over that, you remove what you have put before. So we can't say that we have a very non-uniform adhesion of the copper to the capton, and the sensor is damaged. So functionally speaking, this is not a valid solution for this application. This put us in the situation of looking for some alternatives, like could be the copper electroplating, the using of conductive adhesive, or even the soldering. This is basically because, I mean, the cold spray is good for certain application. In metals, this is perfect, and Cometa and COMPOSITADOUR has it. Has worked on it over the years. But for these very smooth materials, it is not stiff enough to have the deposition. So, well, it's a lesson learned from this project. This gives a problem for the next step, that was the machining of the external connection. That this task in principle was part of the MICROLAN part, but what we did in change is looking for some alternatives for putting the connectors. Those were trying to find a proper conductive adhesive that could be applied, withstand the high temperatures later on in the curing process of the composite. We tried as well with different kind of solderings, because as well, okay, the temperature is 180 degrees in the oven, so we cannot use the typical soldering that is more easily accessed, but we use some solderings that has very high melting points, and we tried with that, but the solution was not very good, because as well the very thin substrate laminate that we have. Finally, we as well continuing with the use of conductive adhesive, we try to put some connectors. That is something that, well, it works quite well, but needs to be considered in the design before putting them in the composite. So we finally decided just going to put in the adhesive, in the conductive adhesive in the contacts, and finalizing the project with that. The final conclusions for all of this, I start by the end. The TRL4 is obtained. We have complete the testing successfully. We see that the solution is feasible, and next step will be the escalation. For that escalation, it's true, we have to improve some of the points, because I mean it's somehow a very manual process that needs some points to be fine-tuning. But apart from that, the FComp project is a success in its definition. We have a feasible design for the sensor. We have obtained a process for manufacturing a very good selection of the materials. In this case, we will go with the polyamide, with the Kapton. And we have learned certain points that has to be considered when putting this into a final solution. First of all is when doing the selection of where we want to put the sensor, we have to consider it since the design phases. I mean, we have to make our stress analysis considering that we are going to have this reduction on the stress capabilities of the part in a local area. As well, the location of the connector has to be considered in the design because it has to be an accessible point, but as well a point that somehow we can have the access to the harness or to the machining point. Basically, this is all the conclusion. We are quite happy. We have obtained this TRL4, and we have thought that this solution or aim will be trying to go to a further step and integrating it in different industries. Our idea is that for aeronautics is quite straightforward. We can include in all the composite structures that are in a plane, just for health monitoring or even in-flight check. We can see if we are flying in a storm, for example, what are the maximum loads that we are seeing in that moment. I mean, it's a very unlikely case nowadays that having a breakage in flight, but okay, we can have it. But as well, it's more related with the maintenance. I mean, we can optimize the times between each maintenance moment, and as well, it can be done. We did not need to stop the plane flying. I mean, the check is already done just by the structure itself. Okay, I have consumed this life. I'm okay. I'm not okay. You don't need to stop and doing further analysis, inspections, and so that finally it's money. For space, for example, is more or less the same. Nowadays, we are seeing now very frequently. This is true that SpaceX, for example, is flying its rockets, its Falcon 9, going back and forward. They reduce the rocket. You can see the photo. They are landing, both of them. This is for the Falcon Heavy, indeed, because they are two. They recover the rockets and they reuse it. They reuse them. How many times can you reuse them? If you measure the stresses that has suffered this structure during the flight, you can easily decide whether you can extend the life of the rocket, or in that case, for example, you need to scrap it because I don't know why you have had a flight with a lot of turbulence, the pressures were whatever, and then the rocket is more damaged. So that as well will help in saving money. For the urban mobility, we have seen that there are applications currently especially in the electric car, where the composite material is more used, and especially in this car sharing of that is in the big cities is very common. The owner of the cars can check how good or how bad is the driver, just measuring what are the stresses that are seen in the car. This way, you can change the tariffs. You can the cost for the user can be higher or lower depending on how good or how bad he or she is. This is the same for the insurance. They can double check either the event where something is broken has happened in a certain moment or not. So this will change as well the tariffs that are applied to the users. And a final future application for us is in new space and UAVs, where the volumes are very low and the need of integrating the sensors is very high. In this case, for example, in the CubeSat, you can see there is a small patch antenna that can be embedded in the composite, as well some other sensors, the strain gauges, but as well the electronics can be put inside the composite, adding this additional functional to a part that has to be already there. So we think this is a very promising application that can be used as well for these new UAVs and new space system. So that's all. Thank you. Hope you have understand well what I have tried to explain. But in any case, we are here now. We have some minutes, no, Martin? Yes, for answering some questions or generating some debate. I don't know if we have questions in the chat, not, but If not, I don't know, Anaïs, Guillén, do you want to add something? I mean, what is your experience with FComp? What has been the benefits from your companies, from COMPOSITADOUR and from MICROLAN?
So for COMPOSITADOUR, it allowed us to make a state-of-the-art of what is done in the electronic printing and in situ monitoring of composites, because we didn't work on it until the FComp project. So in my case, I learned more from you for the electronic printed and from the machining also. So I think it was a nice project, and we obtained quite good results, beginning results. And there is still some work to do on the mechanical part and optimization of the sensors. So I think it should be nice to continue to work on this, because it is quite innovative in the aerospace industry. So that's all.
Yeah, I fully agree with you. We are in a good position for continuing and getting a very good product and solution for the aeronautics. Guillén?
Yes, don't know if you hear me. I hope
yes.
you do. Well, for us, it's been a pleasure to participate in this project. Research and development projects allows us to learn about the aerospace industry needs and tendencies. Composite machining is a whole new world for us, and this project has allowed us to start to take a few steps on the learning of how these materials have to be machined. The main outcome for us on this project and other we participate in is the knowledge and the know-how we obtain. So in this way, it's been a complete success, as we have learned a lot about not only the machining but also the composites in general. The other outcome is to strengthen our relationship with our French partners, ESTIA. And I would like to thank you, Anaïs. She has made this really easier. And it's been a pity we haven't achieved the main objective, which was revealing the contacts of the printed circuit. But we have been able to obtain a high quality drills on the composite, which make us think, make us believe that in further steps of this project, or this project could be continued by taking this machining from the beginning, take it in mind from the beginning. It's been a really great pleasure to us to participate in this project, and we are open to start whatever projects, aerospace related projects, with you, with NAETEC, with ESTIA, and of course with HEGAN. And we would like also to thank the Euroregion for its help.
Okay, yeah, I think the pleasure is mutual. Martin, I don't know if we have some questions now live. If not, for all the participants, don't be shy. You have our emails in the presentation that Martin or HEGAN will distribute later. You can email us with whatever question you have. We are open. We are more open to develop components with whoever wants them. So this is something that is starting, and we want to continue, because we consider that this proposal can give a differentiation to the parts that integrate them. So yeah.
Can you hear me? Yeah, we've got a question from the chat. Okay, a shy person asked me something. Well, asked you something. I'll read. Okay, I'll read literally. Could be the sensors used in RTM process. I suppose RTM is resin transfer molding. could be the sensors used in RTM process?
They can be used, but as well the process has to be slightly, let's say, modified. The issue is that the placing of the sensor has to be done manually in principle, unless you have a way of doing it automatically. But in principle, for the conditions of the process, it will be okay. And it will be just a matter of trying to define the details for placing it, but it can be done. Bear in mind, and this is something that we would like to highlight, what is difficult in here, for example, will be the introduction of an electronic component in the sensor itself. For that, the solutions are slightly different, and the process, for example, does not go through using an oven. So it depends. It has to be studied in detail which sensor is needed and how we can do it. But in principle, the answer is yes, we can do it.
No more questions via chat.
Okay.
Hey, yeah. Another one. Have you? Oh, well, you've got the question too. Have you envisaged to embed other types of sensors like optical fibers?
Well, for this, the answer, well, Anais maybe can ask, but the answer as well is yes. And this is done not only in aeronautics, but as well in automotive industry. And this is something that is already being done. The optical fiber can be used only for having lights or whatever, but as well for transmission, and as well for using it as a sensor, no, as a distributed sensor along the fibers. This is something that, for example, in the blades of the wind turbines is a very useful solution for health monitoring. And yes, it is something that can be done, and as well, it is already there. So this is Guy Largnac. If you want further detail, and we can discuss, we can put an Anais as well in the loop, and something that we can see in detail.
Well, I think it's we are getting over. I think Angelo, thank you very much. I think it has been a very successful project. I mean, we've been participating in a lot of projects, but in this one, it has been serious. There's a demonstrator. We are ready to go to TRL4. That's I think it's a great success for everybody. Angelo, may I ask Leyre to say something to close the session, because it's 9. It's time.
Yes, for sure.
So Leyre is the project coordinators of NAEN of the Euroregion, and as everybody knows here, this project is co-financed by the Euroregion. Thank you, Leyre, for your closing words. I'm afraid we cannot hear you, Leyre. I don't know why.
Now you can hear me?
Yes. Now, yes.
Okay. So, well, for us, it has been a pleasure to get to know all the partners. The project, we think, is a success. It's one of the cases we can say that really fulfills what we search when we showcase, when we open this call for projects. We want to support, to promote cooperation among partners in the 3 regions. And I think all the projects, all the collaborations you have showcased can increase the development of innovative methods, products, and service. And we wanted to thank you all for your commitment for the success of the project. Thank you.
Okay, thanks a lot, Leyre, for your words. Well, if some of the partners wants to say something now, because it's time to say something, we are recording the session. We are going to upload the video, I hope, to our channels. Okay, so if everyone wants to say something. If not, we can say goodbye and say thank you, everybody. Thank you for NAEN, for the partners, of course, for the people that have been with us today. And see you in the next project, I think. Okay? See you. Bye. Take care.
Bye-bye.